remember are that the voltage given at all time, in any voltage given, is always the line voltage. That is, if they give you a voltage in a question and they didn't specify whether it is phase voltage or line voltage, you must assume that the voltage given is line voltage. If they didn't specify that it is phase voltage, you must assume that it is line voltage. Number two, the voltage is always the reference unless otherwise stated. So for the reference, you don't take any other quantity as the reference. Voltage will always be the reference, not current, not any other quantity. It is the voltage that will be used as a reference, except it is otherwise stated. Voltage will always be the reference. Voltage is always the reference, except otherwise stated. And the voltage given, VL, is always the voltage given. Right. Then number three, in a positive phase sequence, if it is positive phase sequence system, the line voltage will always lead the corresponding voltage by 30 degrees. So like this is a positive phase sequence, the line voltage leads by 30 degrees. If it is negative phase sequence, the phase voltage will lead. That means the line voltage will lag phase voltage by 30 degrees. So if it is positive phase sequence, the line voltage will always lead the phase voltage by 30 degrees. If it is negative phase sequence, the line voltage will lag the phase voltage by 30 degrees. Check also that one from your text. Now, let's move another step further. So when you have a star connected supply, let's say this is a supply, three phase, phase A, phase B, phase C, with the neutral. Right. Now, the current is moving, flowing out. These are supply. Then this is the neutral wire, right, that returns the current. This is our IB and this is our IC. Good. Now, the voltage between this phase and the neutral, we call it the phase voltage, VAN. That is the arrow is pointing at that phase, that line, to this neutral. That is VAN. If it is this VBN, the arrow will point to this and it will be VBN. Our VCN likewise will be VCN. That's the voltage, the phase voltage there. Now, our line voltage will be between the lines, which is like between this and this, between line A and B, we have VAB. Between line B and C, we have VBC. Between C and A, we have VCA. So those are the phase line and the phase voltages being represented. Why this is ZA, ZB, ZC. You find that one in figure 2.9 of your textbook. Figure 2.9 of your textbook. Now, let's move one step further. The the EAN, if you look at a figure that we, if you go back, if you look at the figure that we just dealt with, if we look at the voltage EAN will be EAN sine omega t, if we are taking it as the reference, which is EAN at angle 0 degree volt. Then if you look at EBN, this is a positive phase sequence that we just represented the other time in the phasor diagram. It will be EAN. We are now having EBN sine omega t minus 120 degrees, which is equal to what? Which is equal to EBN at angle minus 120 degrees. Likewise, we have ECN to be ECN at angle 120 degrees voltage. Right. Then if you find the sum of those faces together, that is, if you find the sum of those faces together, that is EA, EB, and EC. The total sum, that is EAN plus EBN plus ECN, right? It will give you what? Our EAN is at, that is, if you add it together, if you have EAN plus our EBN is it will be 1 at angle, the first one is 1 at angle, our EAN is 1 at angle 0. Let's look at the 1 at angle 0, and plus EBN, which is 1 at angle minus 120 degrees, plus ECN, which is 1 at angle 120 degrees. Right. If you add it together, you find it to be equal to 0, which only tells you that the sum of the phase voltages, which are the phase voltages, some of them are equal to 0. Right. Then, now let's look at something more that you are going to need from time to time. That is, if you want to determine the voltage using Kashua's voltage law, let us assume that you have a phase. This is, we are just taking phases A and B, where this is the neutral, and we are saying the voltage across here is, say, VAN, and the voltage across here is VBN. Let us assume we are looking at this like a closed circuit, where we have this one as a VAB. Right. If you want to look at it this way, VAB, this is higher potential, which means if current is flowing, let's take it as a closed circuit using Kashua's voltage law. VAB, this is higher potential. That means current will be flowing from here, and this is higher potential with respect to here. So when the current flows, it comes through here. So VAB plus continue plus VBN. Then when you get here, the current is flowing from here down. That is opposite. That is minus VAN. Kashua's is equal to 0. VAB then will be what? VAN minus VBN. So that is why we derive VAB to be equal to VAN minus VBN. Right. In the same manner, you can conclude that your VCN CA will be equal to what? VCN minus VAN. While your VBC also will be what? VBN minus VCN. You can check that one out in figure 2.11. That is page 21 of your textbook, of your Electrical Engineering Technology textbook, 6th edition, page 21. Thank you.